Somewhere in the dark between stars, something was moving. It had been moving for a very long time, longer perhaps than our sun has been burning, drifting through the cold and the silence of interstellar space with no star to orbit, no gravity to hold it close, no home to return to. It was simply traveling, as ancient travelers do, unhurried, unannounced, and entirely indifferent to the small yellow star it was now approaching from a direction we had never thought to watch. We did not know it was coming. There was no warning, no signal, no whisper from the dark to tell us that something extraordinary was on its way. The universe does not send announcements. It simply arrives. And on a night not so different from this one, while most of the world was asleep and the sky above a network of automated telescopes was clear and deep and full of ordinary stars, it was found. Not by a human eye pressed to an eyepiece, not by a scientist with a hunch or a theory, but by a camera, a patient, tireless, wide-eyed camera that sweeps the sky night after night, cataloguing the countless moving things that drift and wander through our cosmic neighborhood. The camera does not know what it is looking for. It simply looks. And on this particular night, it found something that did not belong. A faint smear of light. Moving faster than it should. Moving in a direction that made no sense if you assumed, as most sensible people would, that this object had been born here, in our solar system, bound by the sun's gravity like everything else we have ever known. The numbers did not add up. The velocity was too high. The trajectory was too steep. Whatever this was, it had not come from here. And in that quiet recognition, in the soft click of a calculation running to its conclusion in some astronomer's terminal in the early hours of the morning, the universe handed us something remarkable. A visitor. A piece of another star system, flung across the galaxy and delivered, almost impossibly, into the narrow window of our detection. A message in stone and ice from a place we will never visit, written in a language we are only just beginning to learn. This is the story of 3i Atlas. Let yourself settle into this for a moment. Let the image form slowly in your mind, the deep black of space, not the friendly darkness of a clear night sky, but the true darkness between stars, a void so vast and so cold that even light takes years to cross it. No warmth. No sound. No sense of direction. Just the distant, scattered pinpricks of other suns, impossibly far away, and in between them, almost nothing. Almost nothing, but not quite. Because the galaxy is not as empty as it seems. Scattered through that immense darkness, moving silently between the stars, are objects we are only now beginning to appreciate. Remnants of planetary formation. Debris from ancient collisions. Comets and asteroids and stranger things, ejected long ago from systems we have never seen, set adrift on trajectories that cross tens of trillions of miles without ever being noticed. They travel through the galaxy the way a single leaf might travel across an enormous ocean, drifting, patient, completely alone, brushing past island after island of starlight without anyone ever knowing they were there. Until now. Until us. Until the moment we built instruments sensitive enough, and surveys wide enough, to catch one of these travelers in the act of passing through. The object we now call 3i Atlas was doing exactly that, passing through. Not visiting. Not stopping. It will sweep through our inner solar system on a trajectory so steep and so fast that it will not be captured, will not be held, will not stay. It is simply passing through the neighborhood of our sun the way a river passes through a valley, shaped briefly by the gravity it encounters, and then gone, continuing outward into the dark on the other side, heading somewhere else, or perhaps heading nowhere at all, just onward, forever. But for this brief window of time, it is here. Close enough to see. Close enough, perhaps, to study. And in that brief proximity, we have the opportunity to ask it questions that no other object in our solar system can answer. Questions about where it came from. Questions about what its home system was made of. Questions about how worlds form around other stars, and what remains when those worlds are disrupted, and how the raw material of planets moves through the galaxy over billions of years. These are not small questions. They are among the largest questions we know how to ask. And 3I Atlas, this quiet traveler from the dark, may carry some of the answers, written in its composition, encoded in its spectrum, painted across its surface by the chemistry of a star system we will never otherwise reach. It helps, when thinking about something this extraordinary, to begin at the very beginning. Not the beginning of the object itself, that story is too long and too ancient to tell in a single night. But the beginning of our awareness of it. The moment of discovery. The quiet, almost accidental instant when a piece of another solar system entered our catalogue and our consciousness simultaneously. The Atlas Survey. That is where this story begins. Atlas stands for Asteroid Terrestrial Impact Last Alert System, and the name tells you something important about its original purpose. It was not designed to find interstellar visitors. It was not built to probe the deep mysteries of galactic ecology or the chemistry of distant planetary systems. It was built for something far more immediate and far more urgent, to watch for asteroids and comets that might one day threaten the Earth. To be the early warning system, the cosmic smoke detector, the patient sentinel scanning the neighborhood for incoming rocks that could do us harm. To do this job, Atlas needs to be wide-eyed and tireless. It cannot afford to be selective. It cannot spend too long staring at one patch of sky when dangers might come from any direction. So it sweeps. Night after night, telescope by telescope, it images the sky in great overlapping swaths, taking multiple photographs of each area separated by short intervals of time. This is the essential trick of asteroid hunting: take a picture, wait a little while, take another picture of the same region, and then compare them. Stars do not move. Background galaxies do not move. But nearby objects, objects within our solar system, objects close enough to be affected by Earth's gravity and the Sun's gravity in measurable ways, those objects do move. They leave a trail. They shift position between one image and the next. And that shift, that tiny displacement against the fixed tapestry of distant stars, is how we find them. The Atlas system operates from multiple sites around the world, spread across different longitudes and latitudes to give it the widest possible coverage of the sky. There are stations in Hawaii, in Chile, in South Africa, in the Canary Islands. Together, they form a network that can image the entire visible sky every 24 hours, or more frequently when the geometry of the Earth and the positions of the telescopes allow it. This is a tremendous capability. Not so long ago, sky surveys of this kind required teams of human observers working through the night, inspecting photographic plates by eye, blinking back and forth between images to detect movement. Now the work is done by algorithms, by software trained to recognize the signature of moving objects, to sort the genuine detections from the noise, to flag the candidates that warrant further investigation. It is a beautiful thing, in its own quiet way. A system of machines and mathematics, spread across 4 continents, watching the sky so that we do not have to watch it every moment ourselves. Patient. Persistent. Never tired. Never distracted. And it was this system, on the night of its detection, that first noticed the faint moving point of light that would eventually become the most discussed object in modern astronomy. The initial detection was, by all accounts, unremarkable in appearance. A point of light. A smear on a CCD detector. A tiny displacement between two images separated by perhaps 30 minutes or an hour. The automated pipeline flagged it as a moving object, assigned it a provisional designation, and sent it along to be confirmed. This is a routine process. Atlas detects hundreds of moving objects every clear night. Most of them are known asteroids, already catalogued, already well understood, simply passing through the field of view and being observed yet again. Some are new discoveries, small rocks in the main belt between Mars and Jupiter, or near-Earth objects worth tracking more carefully. The vast majority are completely ordinary. But some detections, when you look at them more carefully, are not ordinary at all. The first indication that something unusual had been found came from the rate of motion. The object was moving across the sky at a speed that, when combined with its estimated distance from Earth, implied a velocity that was too high. Not slightly too high, not within the margin of error, not a number that could be explained away by some unusual orbital configuration within our solar system. Too high in a way that was immediately and unmistakably significant to anyone who understood what the numbers meant. Velocity is the key to everything in orbital mechanics. Every object in our solar system, every planet, every moon, every comet, every asteroid, is moving at a speed that reflects its relationship to the Sun's gravity. Objects close to the Sun move fast. Objects far from the Sun move slowly. But there is a ceiling, a limit, a maximum speed that any object can reach and still remain gravitationally bound to the solar system. This is called the escape velocity, the velocity at which an object moving outward will just barely escape the Sun's gravitational pull if it never slows down. For an object at the Earth's distance from the Sun, this escape velocity is approximately 42 kilometers per second relative to the Sun. If you find an object moving faster than this, significantly faster, in a way that cannot be explained by a close approach to one of the giant planets or some other gravitational slingshot within the solar system, then you are looking at something that is not bound to our Sun. Something that came from outside. Something interstellar. The calculations done in the hours and days following 3I Atlas's first detection showed that this object was moving at a velocity well above the local escape speed. Its trajectory, when computed with increasing precision as more observations were gathered, described a hyperbola, the open, swooping curve of an object that enters a gravitational system, bends around it, and exits on the other side, never captured, never held. Not an ellipse, which is the closed loop of a bound orbit. A hyperbola. An open curve. A one-way path. This is the geometric signature of an interstellar visitor, and when you see it for the first time in a dataset, when you watch the numbers settle into that shape and understand what they mean, it is an extraordinary moment. The object in your data is not from here. It has never orbited our Sun. It came from somewhere else, somewhere outside the boundary of the solar system, somewhere in the galaxy beyond the furthest reach of the Sun's gravitational dominion. It spent most of its existence in interstellar space, and now, for a brief time, it is threading the inner solar system, bending around the Sun, and heading out the other side. The term that astronomers use for the excess velocity, the amount by which the object's speed exceeds the local escape velocity, is the hyperbolic excess velocity, sometimes written as v infinity, because it represents the velocity the object would have if it were infinitely far from the Sun, where the Sun's gravity has no further effect. For 3I Atlas, this hyperbolic excess velocity was substantial. Large enough to rule out any possibility that this was a solar system object on an unusual orbit. Large enough to confirm, beyond any reasonable doubt, that this visitor had traveled to us from the space between the stars. When this confirmation came through, the astronomical community moved quickly. additional observations were requested and coordinated across multiple observatories around the world. Professional telescopes, including some of the largest ground-based instruments available, were redirected to gather more data. The object was observed in multiple wavelengths. Its position was measured repeatedly, with increasing precision, to nail down the orbit. Its brightness was measured, and the way its brightness varied over time was recorded, to get some sense of its size and shape and rotation. Everything that could be learned in a short time was being learned as quickly as possible, because everyone understood the urgency. This object was not going to stay. The window for observation was limited. Interstellar objects, by their very nature, arrive fast and leave fast. They do not loiter. They sweep through the inner solar system and then they accelerate outward, receding into the dark. Every day of delay is a day of opportunity lost, a chance to learn something irreplaceable that slips away as the object recedes and dims and eventually disappears back into the interstellar medium. The astronomers working on 3I Atlas knew this, and they worked with an urgency that you can hear in the papers they published and the announcements they made, a sense of excitement tinged with the knowledge that time was short. Now, let us rest with the naming for a moment, because the name itself tells a story worth savoring slowly. The convention for naming interstellar objects is relatively new, because the objects themselves are a relatively new discovery. Before the detection of the first confirmed interstellar visitor in 2017, the naming convention did not need to exist. We simply assumed, with reasonable confidence given centuries of observation, that all the objects we detected in our solar system had been born here, formed from the same disk of gas and dust that gave rise to the planets 4.5 billion years ago, and were moving in bound orbits around the Sun. We had no category for visitors from outside, because we had never seen one. The designation system uses the prefix I for interstellar, and a number indicating the order of discovery. The first interstellar object detected was designated 1I, the second 2I, and this newest arrival is 3I. After the I comes the name of the Discovery Survey or the person or team that first reported the detection, in this case Atlas, giving us the full designation 3I Atlas. There is something quietly beautiful about this naming convention. It is a record of firsts, of milestones in human awareness. 1I for the first time we ever knew, with certainty, that a piece of another star system was passing through our own. 2I for the second time, confirmation that the first was not a fluke. And now 3I, and we are beginning to wonder how many more there will be, how frequently these visitors arrive, how many have already passed through undetected in the centuries before our telescopes were sensitive enough to notice them. The number 3 is young enough to still feel extraordinary. It is still early days. We are still learning how to look, still calibrating our instruments, still building the intuition for what an interstellar object looks like in the data. But the numbers will grow. The surveys are getting better, the detectors more sensitive, the sky coverage more complete. With the Vera C. Rubin Observatory and its legacy survey of space and time now coming online and beginning to reach its full capability, astronomers expect to detect interstellar objects more frequently, perhaps several per year in the coming decades. What was once a once-in-a-generation event may become something almost routine. Almost routine. Not quite. Because no matter how many of these objects we eventually discover, the first few will always carry a special weight. The first time we realized the galaxy was sending us samples of its other worlds, that is a threshold humanity crossed only very recently, and the feeling of that crossing has not yet faded. Think of it this way, if you will, as you feel yourself settling more deeply into this quiet. Imagine that you live in a small village on an island, and your entire life you have known only the things that were born on that island. The rocks and the trees and the animals and the rivers, all of it familiar, all of it explainable by the island's own history. And then one day something washes up on the beach. A piece of wood. A fragment of pottery. Something clearly made or shaped by forces and materials that do not exist on your island. And in that moment, you understand something you had known abstractly but never truly felt, that your island is not all there is. That out there, across the water, beyond the horizon, there are other places with their own rocks and their own trees and their own histories. And this fragment on your beach is a message from one of them. That is what 3i Atlas is to us. A fragment washed up on our cosmic beach. A piece of pottery from another world, shaped by forces and chemistry and history that we are only beginning to imagine. It does not speak in words. It speaks in photons, in spectral lines, in the mathematics of its trajectory. But if we listen carefully enough, and we are listening, as carefully as we know how, it may tell us things about the universe that no other messenger could carry. The Atlas system that found this object deserves a moment of quiet appreciation in its own right, because it represents something remarkable about this particular era of scientific history. We are living through a revolution in sky surveys, a transition from the era of individual observers and targeted observations to the era of wide-field robotic astronomy, where the sky is watched continuously by machines that never sleep and never lose patience. For most of the history of astronomy, observing time was precious and finite. Telescopes were operated by humans, and humans needed to sleep, and during the day the sky was unavailable, and clouds disrupted observations, and the most powerful instruments were always in demand for the most scientifically urgent projects. You could not simply point a large telescope at the entire sky and wait to see what moved. You had to choose what to look at, because you could not look at everything. The new generation of sky surveys changes this equation profoundly. Atlas, and systems like it, are purpose-built to do the thing that was previously impossible, to monitor the entire sky, continuously, with enough sensitivity to detect faint moving objects, and with enough data processing capability to sort through the resulting flood of information automatically. These systems do not choose what to look at. They look at everything. And in looking at everything, they find things that targeted observations never would have caught, things that were in the wrong part of the sky at the wrong time, things that nobody thought to look for because nobody knew they existed. Interstellar objects are exactly this kind of discovery. Nobody was looking for them before ʻOumuamua, because nobody had strong reason to believe they would be detectable. The theoretical prediction that objects should occasionally pass through from interstellar space existed, tucked into papers about the Oort cloud and solar system formation, but the predicted flux rates were uncertain by orders of magnitude, and the objects were expected to be faint and fast-moving and easily missed. The surveys that found Oumuamua, and Borisov, and now Atlas, were not designed with interstellar objects in mind. They found these objects as byproducts of doing something else, watching for threats, cataloging the solar system, building a census of the minor bodies that populate the space around us. This is one of the beautiful accidents of science. You build a tool for one purpose, and it reveals something you were not expecting. You sweep the sky for dangerous asteroids and you catch a message from another star. You catalog the minor bodies of the solar system and you find a traveler that does not belong to the solar system at all. The universe cooperates with your curiosity in ways that are sometimes startling, sometimes humbling, and almost always, in the end, wonderful. In the days and weeks following the initial detection and confirmation, 3i Atlas became one of the most observed objects in the sky. Telescopes on every continent were pointed at it. Space-based observatories were maneuvered to capture its light. Amateur astronomers with sufficiently large instruments joined the effort, contributing observations that added to the growing dataset. The object was observed at optical wavelengths, at infrared wavelengths, and where possible at ultraviolet wavelengths as well, each window revealing different aspects of its nature. What emerged from these early observations was a picture that was, in some ways, expected, and in other ways deeply intriguing. The object had a coma, a diffuse halo of gas and dust surrounding the nucleus, the signature of outgassing, of volatile materials being heated by the sun and sublimating off the surface. This made it look, in a general sense, like a comet, an active body with a bright central condensation and a spreading envelope of ejected material. This was already more than could be said for one Oumuamua, which showed no coma at all, no visible sign of cometary activity, and which therefore presented a much more mysterious face to the observers who studied it. 3I Atlas, at least, was willing to share something of itself. It was exhaling, releasing material into space, and that material carried chemical information that spectroscopes could read. The brightness of the object, combined with estimates of its distance and assumptions about how reflective its surface might be, suggested that its nucleus was substantial in size, not a tiny pebble but a body of meaningful dimensions, though the coma made precise measurement of the nucleus itself challenging. The coma is both a gift and a complication. It is a gift because the gas and dust in the coma carry compositional information that is relatively easy to analyze spectroscopically. It is a complication because it obscures the nucleus, wrapping it in a fuzzy envelope that makes it difficult to measure the solid body directly. This tension, between the information the coma provides and the information it obscures, is one of the central challenges of studying active cometary objects, whether they are from our solar system or from beyond it. Astronomers who work on comets are well accustomed to navigating this tension, teasing apart the signal from the nucleus and the signal from the surrounding coma, using various techniques to separate what the solid surface is telling them from what the evaporating material is saying. For 3I Atlas, these techniques were applied with particular urgency, because every observation was precious and the clock was running. The object was bright enough, and active enough, and interesting enough to command attention from the most powerful instruments available. And what those instruments were beginning to show was deeply interesting, not just the confirmation that this was an interstellar visitor, which was already established beyond doubt by the orbital mechanics, but hints and suggestions about the chemistry of its home system, about the conditions under which it formed, about the processes that had eventually set it adrift on its long journey through the galaxy. But before we go deeper into what 3I Atlas is made of, let us first follow its trajectory backward through space and time, tracing the path it has traveled to reach us, trying to answer the question that every human being who has ever looked up at the night sky would naturally ask when they learn that something has arrived from outside the solar system. Where did it come from? That question hangs in the air like a breath in cold night. Where did it come from? And as you hold that question gently in your mind, let yourself feel the enormity of the distance implied by it. Not the distance between cities, or continents, or even between the Earth and the Moon. Not even the distance between the Earth and the Sun, or between the Sun and the distant edge of the Oort cloud. The distance implied by that question is the distance between stars, the interstellar gulf, measured in light years, measured in the time it takes light itself to cross it. And somewhere across that gulf, in a system of worlds we may never name, this visitor was born. Let us hold that thought softly as we approach the second great chapter of this story. Because to understand where 3I Atlas came from, we need to understand how its trajectory can be unwound backward through time, mathematically reversed. The equations of orbital mechanics run not forward into the future but backward into the past, tracing the path this object followed through the galaxy until we can point, at least approximately, in the direction from which it came. This is the science of astrometry and orbital dynamics, the precise measurement of position and velocity, and the mathematical machinery that turns those measurements into a history. It is not a simple calculation. It requires precise measurements of the object's position at multiple times, careful accounting for all the gravitational influences that have bent its path as it moved through the solar system, and a deep understanding of the structure of our galactic neighborhood. But it can be done. It has been done for the previous interstellar visitors, with results that were illuminating even when they were not definitive. And it is being done for 3i Atlas, with data pouring in from observatories around the world, each new measurement refining the orbit a little more, narrowing the uncertainty a little further, bringing the origin story of this ancient traveler into slightly sharper focus. The mathematics of hyperbolic orbits, when you think about them slowly and let their meaning settle in, are quietly beautiful. An ellipse is a closed story, a narrative that returns to its beginning, a planet going around and around its star in a path that never ends. A parabola is the edge case, the perfect boundary between bound and free, the orbit of an object that will just barely escape to infinity, asymptotically slowing as it recedes. And a hyperbola is the open story, the one that has a beginning and an end but no repetition, the trajectory of something that arrives from infinity and departs to infinity, touching the gravitational influence of a star for just a moment in the vast sweep of cosmic time. 3i Atlas is writing a hyperbola around our Sun. And the shape of that hyperbola, the precise angle of its asymptote as it approaches from the direction of deep space, is a pointer, a directional arrow that, if we follow it backward across the light years, may lead us toward the system that gave birth to this traveler so long ago. The automated pipelines of the Atlas survey, working through the night on computers in Hawaii and in Chile, did not know they were about to make history when they flagged the faint, fast-moving point of light that would become 3i Atlas. They were doing what they always do. Looking. Measuring. Comparing. Sorting. The discovery was quiet, as most great discoveries are. Not a trumpet fanfare but a notification. An entry in a database. A flag in a software output. A number slightly out of range. And then, in the hours and days that followed, as more observations came in and the numbers became clearer and the trajectory became undeniable, the quiet realization spread through the small community of people who were watching the data. Something interstellar had been found. A third visitor. Another message from the dark. The universe, it seems, has more to say than we imagined. The confirmation process for an interstellar object is worth understanding in some detail, because it is not a matter of one observation or one calculation. It is a process of accumulation, of evidence building upon evidence until the conclusion becomes inescapable. A single observation of a fast-moving object might be explained in many ways. Measurement error. An unusual orbit within the solar system. A comet that has received a gravitational kick from Jupiter. Any number of mundane explanations are possible for a single data point. But as the observations accumulate, as the orbit is refined and the hyperbolic excess velocity is confirmed by independent measurements from different observatories with different instruments and different calibration systems, the mundane explanations are ruled out one by one. The probability that the trajectory is consistent with a bound solar system orbit falls toward zero. The eccentricity, the number that describes how stretched an orbit is, where a circle has eccentricity 0, an ellipse has eccentricity between 0 and 1, a parabola has eccentricity exactly 1, and a hyperbola has eccentricity greater than 1, settles to a value comfortably above 1. Not barely above 1, the way a long-period comet perturbed by a passing star might be, but clearly, unambiguously above 1, in the way that only makes sense for an object that arrived from outside the gravitational reach of our Sun. For 3i Atlas, the eccentricity was determined to be significantly greater than 1, placing it firmly in the category of hyperbolic objects, and the direction of its incoming trajectory, its radiance, pointed away from the plane of the solar system in a way that was inconsistent with a solar system origin but entirely consistent with an object arriving from interstellar space. These were not ambiguous results. They were clear and they were confirmed by multiple independent analyses. 3I Atlas is an interstellar object, the third we have ever found. A visitor from another star system, passing through our solar system on a one-way journey that began long before our sun was born. There is a moment, in the process of any great discovery, when the weight of what has been found begins to sink in. When the numbers and the calculations and the confirmations fall away and what remains is simply the recognition, this is real. This is actually happening. Something from outside our solar system, something that formed around another star in a galaxy of 400 billion stars, is close enough to see. Close enough to study. Close enough, if you have the right telescope, to analyze and measure and begin to understand. For the astronomers who worked through the nights following the initial detection of 3I Atlas, this moment presumably came in different ways for different people. For some, it may have come in the middle of a calculation, when the orbit solution first showed the hyperbolic eccentricity and the implications were immediate and visceral. For others, it may have come later, after the confirmations were in and the papers were being written, in the quiet of an office or an observatory dome, looking up at the patch of sky where the object was currently moving and simply holding the knowledge for a moment without trying to analyze it. It came from somewhere else. It has been traveling toward us, across the cold dark between the stars, for how long? That depends on where it came from, and we are still working that out. But the timescales are immense. Even the nearest star to our Sun is over 4 light-years away, and many of the candidate source systems for interstellar objects are much further than that. If 3I Atlas originated in a system 10 or 20 or 50 light-years from here, and if it has been traveling through interstellar space at its current velocity, then it began its journey thousands or tens of thousands or even hundreds of thousands of years ago. It has been in flight for longer than human civilization has existed. Longer than human beings have been fully anatomically modern. Perhaps longer than our species has existed at all. And yet here it is. Here, in our time, in our sky, crossing through the reach of our sun's gravity at precisely the moment when we have the tools and the knowledge to notice it and study it. The timing feels almost impossibly fortunate, though of course it is not fortune at all. It is statistics, and it is the accumulation of technological capability. There have presumably been other interstellar visitors passing through our solar system throughout the history of life on Earth, and before that, throughout the history of the solar system itself. We simply did not have the eyes to see them. Now we do. Now we do. This is where we are, as we approach the deeper questions that 3I Atlas invites us to ask. We have an object, confirmed as interstellar, moving through our inner solar system on a hyperbolic trajectory that will carry it back out into the dark. We have observations accumulating, spectra being taken, orbital solutions being refined. We have a designation, 3I Atlas, that places this visitor in the lineage of its 2 predecessors and promises more to come in the years ahead. We have a community of scientists working urgently to extract as much information as possible from the limited window of observation available to them. And we have a universe that has, for the 3rd time in the brief history of our awareness of such things, delivered a piece of itself to our doorstep and allowed us, for a little while, to study it. The darkness outside your window right now, if you are lying somewhere watching this, or listening to it as you drift slowly toward sleep, that darkness is not empty. It is full of objects like this one, ancient travelers on hyperbolic paths, passing through stellar systems without ever stopping, crossing the galaxy over millions and billions of years. Most of them we will never see. Most of them will glide through our solar system in the darkness beyond Neptune, or beyond the Kuiper belt, or even through the inner system itself, at night, when the sky is not being observed, or in directions that our surveys have not yet covered. They are there. They are passing. We simply cannot catch them all. But 3i Atlas we caught. This one, we caught. And as you let yourself sink a little deeper into rest, as the images of dark space and distant stars and the faint smear of light in a telescope image settle gently into your thoughts, hold that knowledge quietly, that somewhere out there, a traveler from another star is arcing through our solar system right now, at this very moment, moving at tens of kilometers per second through the same sun-warmed space that contains the Earth and the Moon and the wandering planets. We found it. We are watching it. And it is telling us things. The story is just beginning to unfold. And so the first question that any careful mind would ask, after the wonder of discovery has settled into something more precise and scientific, is simply this: where did it come from? It seems like such a natural thing to wonder. You see a stone on a path, and you think about who might have placed it there, or where it rolled from, or what hillside it once rested upon. And here we have something so much more extraordinary, an object that has traveled between the stars, that has crossed the incomprehensible darkness of interstellar space, and arrived in our solar system already moving too fast to stay. Of course we want to know where it began. Of course we want to trace the thread of its journey backward through time and through the galaxy, all the way to whatever sun or cloud or system of worlds first released it into the dark. The science of doing this is called orbital backward integration, and it is, in its own quiet way, one of the most beautiful things that astronomers do. The idea is straightforward, even if the mathematics is anything but. You take the object's current position, you take its current velocity, and you run the equations of motion in reverse. You let gravity play backward, like rewinding a film. The Sun's gravity, Jupiter's gravity, the subtle tugs of Saturn and Uranus and Neptune, all of these are accounted for, all of these are run in reverse, and the object's position is walked back through space and time to a moment before it entered our solar system, out past the orbit of Neptune, out into the space between the stars where the Sun's gravity finally becomes too weak to meaningfully deflect the path anymore. And at that point, you can look at the direction the object was traveling and ask, what is out there? For 3i Atlas, this process began almost immediately after its interstellar nature was confirmed. Teams of astronomers around the world, working with the preliminary orbital data from Atlas and the rapidly accumulating follow-up observations, began the work of tracing the object's path backward through the solar system and out into the galaxy. And what they found is something that will take us a few quiet moments to fully appreciate together. The direction from which 3i Atlas appears to have arrived, its so-called radiant, which is the point on the sky from which its trajectory, when traced backward, appears to originate, lies in a particular part of the celestial sphere, in a region of the sky that corresponds to a specific direction in our galaxy. Now, this does not immediately tell us which star system sent it. The galaxy is immensely deep, and there are stars scattered across every direction we might look. But it does constrain things. It gives us a line to follow, a direction of origin, a compass bearing through the cosmos. What makes this analysis delicate, and what requires such careful mathematical treatment, is the fact that both the object and whatever star system it came from have been moving through the galaxy for the entire duration of 3i Atlas's journey. Stars are not fixed. They orbit the center of the galaxy, they drift through the stellar neighborhood, they change position over thousands and millions of years. So if 3i Atlas was ejected from a distant star system, say, 1,000,000 years ago, that star system is no longer where it was when the object left. It has moved significantly. And so simply tracing the object's path backward in a straight line will bring you not to where the star is now, but to where it was then, in the past, which might be a very different location in the sky. This is why astronomers must account for what is called the peculiar velocity of stars, their individual motions relative to the local standard of rest, the average motion of stars in our galactic neighborhood when they try to identify candidate source systems. They have to model not just the path of 3i Atlas, but the past trajectories of many nearby stars, and look for close approaches. Look for moments in the past when 3i Atlas's extrapolated path intersected with a star's own past position at a time and distance that would make it plausible for that star to have been the origin. This is painstaking work. It requires excellent data on stellar positions and velocities, data that has improved enormously in recent years thanks to the Gaia Space Observatory, Europe's extraordinary mission that has mapped the positions and motions of nearly 2 billion stars in our galaxy with unprecedented precision. With Gaia data in hand, astronomers can now perform backward integration with a level of accuracy that was simply impossible before, and can test dozens or hundreds of candidate stars as potential sources for an interstellar visitor. For 3i Atlas, as these calculations have been carried out and refined with each new round of observations, certain candidate star systems have emerged as worth examining more closely. The caveat that must be held gently in mind is that this is still an active and evolving scientific conversation. Orbital data improves as more observations are gathered, and the list of candidates shifts as the numbers are refined. But the analysis is underway, and it is pointing in directions that are deeply interesting. Without naming specific candidates prematurely, since those details are still being worked out with the precision they deserve, what we can say is that the general direction of origin places 3i Atlas as coming from within the galactic disk, not from the halo above or below the plane of the Milky Way, but from within the busy, star-rich neighborhood where most stars live, and where planetary systems form with the greatest frequency. This is already telling us something. It suggests that 3i Atlas is not an ancient relic from the early universe, not something from a distant primordial era of star formation, but rather something from the same general galactic environment in which we ourselves exist. A neighbor, in cosmic terms. A traveler from a place that is not so different, in broad strokes, from our own corner of the galaxy. The hyperbolic eccentricity of 3i Atlas's orbit offers its own form of storytelling. Eccentricity, in orbital mechanics, is a number that describes the shape of a path. A perfect circle has an eccentricity of 0. An elongated ellipse has an eccentricity between 0 and 1. A parabola, the knife-edge boundary between a bound and unbound orbit, has an eccentricity of exactly 1. And anything above 1 is a hyperbola, an open curve that never closes, a path from which the object will escape, moving faster than the local escape velocity even at infinite distance. For objects bound to our solar system, no matter how elongated their orbits, their eccentricity is always below 1. For 3i Atlas, as with the 2 interstellar visitors that came before it, the eccentricity is measurably, decisively above 1. This is the mathematical signature of interstellar origin. This is the proof written in the numbers. But the specific value of the eccentricity matters too, not just whether it is above 1 but by how much. A very high eccentricity means the object was traveling very fast relative to the Sun even before the Sun's gravity began to accelerate it, which implies that it was moving quickly through the local interstellar medium, which in turn suggests either that it was ejected with considerable energy from its home system, or that it comes from a star system whose velocity relative to ours is quite large, or some combination of both. The hyperbolic excess velocity, the speed the object would have at infinite distance from the Sun, the speed that is the true signature of its interstellar motion stripped of the Sun's gravitational influence, carries in it, encoded like a message, information about where this object came from and how it was set free. For 3I Atlas, the hyperbolic excess velocity has been measured to be quite substantial, enough to narrow down the range of plausible source scenarios, enough to help inform those backward integration calculations, enough to suggest that this is not a lazily drifting fragment but something that was sent outward with purpose, or at least with force. Whether that force was the gravitational kick of a passing planet, the catastrophic disruption of a collision, the slow erosion of a debris disk as a star system aged, or some other mechanism entirely, that is something the orbital analysis alone cannot fully answer. But it sets the boundaries. It defines the space of possibilities. There is something almost meditative about the act of tracing an orbit backward through time. You are, in a sense, reading a history that the universe has written in motion. Every object in space is a message from its past. Every trajectory carries information about the forces that shaped it, the encounters it survived, the distances it crossed. And for an interstellar object like 3I Atlas, that history is especially rich and especially ancient, stretching back not just to the formation of our solar system but to the formation of some other system entirely, somewhere else in the galaxy, around a star we may or may not have ever catalogued, shining in a direction we may look up at on a clear night without ever knowing that this tiny point of light is where our visitor began its journey. That thought is worth sitting with for a moment, the idea that somewhere in the night sky, visible perhaps to the naked eye or perhaps only through a telescope, there is a star that once held 3I Atlas within its gravitational embrace. A star whose planetary system, long ago or perhaps not so long ago, produced the material that eventually became this object. And that star is still shining. It does not know its traveler has arrived. It does not know we are watching. It simply burns, as stars do, patient and indifferent and beautiful. And now, as that thought drifts slowly through your mind like light through a distant nebula, let us turn from the question of where 3I Atlas came from to the question of what it might be, or rather, let us approach that question by first looking at the two visitors that came before it, the two interstellar objects that have preceded 3I Atlas in our scientific understanding and in our imagination. Because to understand what 3I Atlas might be, and why it matters so much, it helps enormously to understand what 1I Oumuamua and 2I Borisov were, and what they taught us, and how they surprised us, and how they continue to puzzle and inspire the scientific community in ways that have not yet been fully resolved. Let us begin with Oumuamua. The name is Hawaiian, meaning something like a messenger from afar arriving first or to scout, and it was given in honor of the Haleakala Observatory in Hawaii where the object was first detected. It was discovered in October of 2017 by the Pan-STARRS telescope survey, and when astronomers first began to examine its orbit, what they found was unmistakable and unprecedented. This object was moving on a hyperbolic trajectory, definitively unbound from the solar system, traveling at a speed that placed its origin firmly outside our solar system. It was the first interstellar object ever confirmed. A genuine first-in-human history discovery. The scientific community reacted with a mixture of excitement and scrambling urgency, because Oumuamua had already passed closest approach to the Sun by the time it was discovered. It was already heading outward, already on its way back into the void, and the window for observation was closing fast. Telescopes around the world turned toward it with whatever time they could spare, gathering as much data as possible before the object faded beyond reach. And what those observations revealed was strange. Profoundly, tantalizing strange. Oumuamua was, first of all, unlike any solar system object ever observed. Its brightness varied dramatically and periodically as it tumbled through space, flickering in and out like a lighthouse, with a variation of nearly a factor of 10 in brightness over each rotation cycle. This extreme variation in brightness is what told astronomers something remarkable about its shape. When an object tumbles in space, it reflects more sunlight when presenting a larger cross-section and less when presenting a smaller one. For the variation to be as extreme as Oumuamua's, the object's longest dimension would have to be roughly 5 to 10 times its shortest dimension. It was, by any ordinary measure, extraordinarily elongated. Something like a cigar, or a pancake, the precise geometry was debated, with some researchers favoring a cigar-like prolate shape and others arguing that a flat, disc-like oblate shape fit the data better. But either way, it was not round. It was not roughly spherical, as most solar system small bodies tend to be above a certain size. It was radically elongated, in a way that had never been seen before in any natural astronomical object. This alone would have been remarkable enough to occupy astronomers for years. But then came the second surprise, and this one was deeper, more puzzling, and more enduringly controversial. As Oumuamua moved through the solar system, astronomers tracked its position with exquisite precision, comparing where it actually was to where the laws of gravity predicted it should be. And they found a discrepancy. A small but definite, impossible to explain away discrepancy. Oumuamua was accelerating beyond what gravity alone could account for. It was being pushed by something. Something beyond the influence of the sun, beyond the gravitational tugs of the planets. Something non-gravitational. In a solar system comet, you would immediately suspect outgassing. When a comet approaches the sun, the heat causes volatile ices, water, carbon dioxide, carbon monoxide, to sublimate from the surface, turning directly from solid to gas and streaming outward into space. This streaming gas acts like a tiny rocket engine, pushing the comet in the opposite direction. It is called cometary outgassing or non-gravitational acceleration, and it has been measured in comets for a long time. So the natural first hypothesis for Oumuamua was the same: it must be outgassing, and the outgassing is pushing it. But there was a problem. A significant problem. No outgassing was ever detected from Oumuamua. No coma, the fuzzy halo of gas and dust that surrounds an active comet, was ever observed. No tail was ever seen. Every sensitive instrument pointed at Oumuamua looked for the telltale signatures of sublimating volatiles, and found nothing. The object appeared to be bare, stark, inert, a solid body with no obvious source of cometary activity. And yet it was accelerating. The scientific papers that followed occupied a long and fascinating spectrum of hypotheses. Some researchers proposed that Oumuamua might be outgassing hydrogen, molecular hydrogen, H2, which would be nearly impossible to detect with the telescopes and instruments available, but which could explain the non-gravitational acceleration if present in sufficient quantities within the object's interior. Others proposed more exotic explanations. A thin, flat, sail-like object, perhaps a fragment of some larger body, or even, in the most provocative and widely discussed hypothesis, an artificial structure of some kind, could be accelerated by radiation pressure from the sun, the gentle but cumulative push of sunlight. For a sufficiently thin and large object, radiation pressure is not negligible. And the geometry of Oumuamua that the brightness variations implied, flat, extended, thin, was at least consistent with something that radiation pressure could meaningfully accelerate. This last hypothesis, the suggestion that Oumuamua might be artificial in origin, was not put forward frivolously. It was offered by serious scientists, including Avi Lieb at Harvard, and it was offered with appropriate scientific hedging as a hypothesis to be considered among others, not as a claim of certainty. And while the scientific mainstream did not adopt it as the most likely explanation, the conversation it started was valuable, because it forced the community to rigorously examine what we could and could not know about this object, what the data did and did not rule out, and what we would need in order to make more definitive claims. What Oumuamua left us with, in the end, was not resolution but wonder. It departed, it faded, it crossed the outer solar system and headed back into the darkness between the stars, and we were left with a handful of observations, a cluster of hypotheses, and no definitive answer to what it was. It was, in a sense, the universe offering us a puzzle it was not yet ready to solve. A riddle written in light curves and orbital anomalies, posed in the few weeks when the object was close enough to observe, before the distance opened up and the signal dropped below our ability to detect. And then came the second visitor. ʻOumuamua Borisov was discovered in August of 2019 by Gennady Borisov, an amateur astronomer in Crimea who had built his own telescope and who, through a combination of skill and dedication and the kind of patient watching that astronomical discovery so often requires, caught the faint smear of light that turned out to be the second interstellar object ever found. The ʻOumuamua designation marks it as the second interstellar object, the ʻIn standing for interstellar in the naming convention that the International Astronomical Union had established after Oumuamua forced them to think about how to name such objects. And Borisov, of course, for the discoverer. Borisov was different from Oumuamua in almost every observable way, and that contrast was immediately illuminating. Where Oumuamua had been bizarre and unprecedented, Borisov was familiar. Reassuringly, productively familiar. It had a coma. It had a tail. It was visibly active, sublimating volatiles as it approached the Sun, behaving in every outward respect like an ordinary comet. Not a solar system comet, of course, its orbit was hyperbolic, its interstellar origin confirmed, but something that looked and behaved like a comet, something whose basic nature felt like solid ground compared to the quicksand of Oumuamua's mysteries. The composition of Borisov was studied extensively, and what astronomers found was striking in its ordinariness. The coma of Borisov contained water, carbon monoxide, various other molecules that are common in solar system comets. The color of the nucleus fell within the range seen in comets from our own Oort cloud and Kuiper belt. The ratio of dust to gas in the coma was normal, by the standards of solar system comets. In almost every compositional measurement that could be made, Borisov looked like a comet from our own solar system, simply a comet that happened to have formed around a different star. This was a profound result. It suggested that the processes by which comets form, the accretion of volatile-rich planetesimals in the cold outer regions of a young stellar system, are universal. The same chemistry, the same building blocks, the same general physics operating in the same general way, producing objects that are compositionally indistinguishable from what forms in our own backyard. It suggested that the galaxy is, on a chemical level, a relatively uniform place. That the water, ice and carbon dioxide and organic molecules that we find in our comets are not unique to our solar system, but are a generic product of the star formation process wherever it occurs. Borisov was also observed for much longer than Oumuamua, because it was discovered while still approaching the Sun, before it reached closest approach, giving astronomers months of observation time rather than weeks. And crucially, Borisov did not exhibit any anomalous non-gravitational acceleration. Its path through the solar system was accounted for by gravity and by normal cometary outgassing to a degree that required no exotic explanations. It was strange because of where it came from, but it was behaving exactly as expected once we accepted that basic strangeness. In a way, Borisov answered one of the questions that Oumuamua had raised without answering. Oumuamua had shown us that interstellar objects exist, that they pass through our solar system, that they are detectable with modern surveys. But its exotic nature had left open the question of whether interstellar objects would, in general, be bizarre and unpredictable, whether Oumuamua was representative of a whole class of strange interstellar exotica, or whether it was an outlier. Borisov, by being so normal, suggested that perhaps Oumuamua was the outlier. Perhaps the general run of interstellar objects are cometary, familiar, products of ordinary planetary system formation processes, and Oumuamua was an exception, a curiosity, a cosmic anomaly that will be puzzled over long after 3I Atlas and dozens of future interstellar objects have been catalogued. But 2 data points are barely enough to form a pattern. 2 visitors is 2 more than we had before 2017, but it is still a vanishingly small sample from which to draw conclusions about what interstellar objects generally are. Each new detection adds to the sample. Each new visitor gives us more information about the range of possibilities, the diversity of what the galaxy sends our way, the variety of objects that planetary systems produce and eject into the interstellar medium. And this is where 3I Atlas becomes so important and so exciting, and so worth watching with the careful attention of science and the open wonder of curiosity. Because 3I Atlas is the third. And the third data point, in any scientific inquiry, is when patterns start to become discernible. Or when the absence of a pattern becomes significant. Or when something so unexpected appears that the first 2 points are thrown into a new light entirely. What we know about 3I Atlas so far, at this stage of observation, already places it in an interesting position relative to its 2 predecessors. In some ways it appears to share more characteristics with Borisov than with Oumuamua. There are indications of cometary activity, of a developing coma, of the kind of volatile-rich nature that would cause an object to respond to the sun's heat without gassing. This would make 3I Atlas the second interstellar comet, following Borisov, which would be a meaningful pattern, 2 out of 3 confirmed interstellar objects being cometary in nature, with Oumuamua as the odd one out. But the picture is not quite so simple, because 3I Atlas has its own characteristics, its own particular measurements and properties, that distinguish it from Borisov and make it interesting in its own right. The size of 3I Atlas, for instance, appears to be substantially larger than either of its predecessors. Estimates based on its brightness and assumed reflectivity suggest that it may be several times larger than Borisov, which was itself estimated to be roughly a kilometer across. If 3I Atlas is indeed as large as early estimates suggest, it would be the largest interstellar object yet detected, which is itself significant. A larger object carries more material, offers more surface and volume for composition analysis, stays observable for longer as it moves through the solar system, and may exhibit more dramatic cometary activity as it approaches the Sun. The size also carries implications for what kind of object this is and how it came to be. Very large cometary bodies, objects that are multi-kilometer in extent and rich in volatiles, are not small, unremarkable fragments. They are substantial pieces of a planetary system's infrastructure. Their ejection requires significant dynamical events. Something meaningful had to happen in the system that produced 3I Atlas to send something this large into interstellar space. A gravitational encounter with a giant planet, perhaps. A close passage by another star that disrupted the outer regions of a planetary system. Some cataclysmic event in the birth environment of a young star system, where the chaotic dynamics of early planetary formation regularly fling objects of all sizes in all directions. This is one of the deep questions that 3I Atlas raises, and that the observation campaign underway is attempting to address. The more precisely we can characterize this object, its size, its composition, its rotation state, its activity level, the structure of its coma if it has one, the more we can say about what kind of system it came from, and what kind of event sent it on its way. There is, as well, the question of whether 3I Atlas shows any anomalous non-gravitational acceleration, the defining strange characteristic of Oumuamua. This is something that can only be determined with sustained, precise astrometry, careful, repeated measurements of the object's position over weeks and months, compared against the predictions of purely gravitational models. If 3I Atlas stays on the track that gravity predicts, modified only by normal cometary outgassing forces that can be independently verified through the detection of gas and dust, then it joins Borisov in the category of the explainable. If it deviates from gravity in ways that cannot be accounted for by observed outgassing, then the mystery that began with Oumuamua deepens significantly. The scientific community is watching for this with careful eyes and patient instruments. It takes time to accumulate enough high-precision position measurements to detect a small but persistent deviation from a purely gravitational orbit. The object needs to be tracked across enough of its arc, and the measurements need to be precise enough to distinguish a real non-gravitational acceleration from the normal uncertainties that come with observing a faint, moving, somewhat fuzzy object across the depths of space. But as the weeks and months of observation accumulate, as the dataset grows and the orbital solution refines, the answer will emerge. And it will be telling, whatever it is. What the three interstellar objects together are beginning to sketch for us is the outline of something profound and important, a picture of the galaxy as a place of exchange, of sharing, of objects moving between star systems over vast timescales, carrying with them the chemical fingerprints of the worlds that made them. They are, these three travelers, the first ambassadors we have been able to examine, the first objects from elsewhere that we have detected crossing our threshold. And each one has told a different story, and together the three stories are beginning to add up to something. There is, held quietly within all of this science, a kind of philosophy that is hard to avoid. The fact that interstellar objects exist, that they are numerous enough to be passing through our solar system regularly, that they come from the same kinds of planetary systems that the galaxy produces everywhere, that they carry the same chemistry we see in our own comets, all of this speaks to a universe that is not a collection of isolated islands, each solar system alone and apart from all others, but something more connected. A universe where material moves between systems. Where the building blocks of planets and comets and perhaps even life are not unique to any one place but are distributed, shared, spread across the galaxy by the dynamics of gravity and ejection and the long patience of interstellar travel. 3I Atlas is not just a rock. It is a message. And the message, so far, reads something like this: we are not so different from what is out there. The galaxy makes things that look like what we know. And it sends them to us so that we might know this. Let that thought settle gently, the way a leaf settles onto still water, without disturbing anything, simply coming to rest. The visitor from another star is out there right now, in the sunlight that is warming it, crossing the space between the planets, and we are watching it with every instrument we have. We are reading its message as carefully and completely as we can. And the story it is telling us is still unfolding, still being written in the data that flows from telescope to computer to mind, in the patient accumulation of science that is, at its best, one of the most extraordinary things that humans have ever learned to do. The night sky above you, if you could see it through whatever ceiling is above you now, is full of points of light. And those points of light are not just beautiful. They are not just ancient. They are connected to us in ways we are only now beginning to understand. They send us things. We send light back to them, unknowingly, with every lamp that burns at night, every city that glows from space. And occasionally, when we are lucky and our surveys are running and the conditions are right, they send us something we can hold in our instruments and study and puzzle over and wonder about for years and decades to come. 3i Atlas is one such gift. The third in living memory. The third in the history of our species. And almost certainly not the last. Let yourself breathe a little more slowly now. Let the vastness of what we have been talking about wash gently over you, not as something overwhelming, but as something spacious and quiet and full of possibility. The galaxy is immense, and it is ancient, and it is busy with the movement of things we are only beginning to learn to see. And we are here, on this small warm planet, with our telescopes and our mathematics and our curiosity, and we are learning. Slowly, carefully, one visitor at a time, we are learning what the galaxy is made of and how it works and what it is saying. And that, on any night, in any season, under any sky, is enough reason to let the mind go quiet and the body rest and the wonder do its gentle work, the way starlight does its work, traveling enormous distances to arrive, softly, without fanfare, and illuminate just enough of the dark to make the next step possible. The story continues. The visitor moves. The instruments watch. And you, here, now, can rest in the knowledge that the universe is being carefully and lovingly attended to by the people whose job it is to pay attention, so that you, in this moment, can simply be still and breathe, and let the stars be as far away and as beautiful and as full of mystery as they have always been. The remaining sections flow now, gently, like the tail of a comet drifting through the cold interior of the solar system, slowly dissipating into the dark, leaving behind only light and the memory of passage. We have spoken of what 3i Atlas is, and where it came from, and what the first two interstellar visitors taught us, and what the composition of this third traveler might reveal about the chemistry of a world we have never seen and may never visit. We have spoken of the galaxy as a living system, cycling matter between stars over timescales so vast they erase the distinction between history and myth. And now, in these final passages, we arrive at the most urgent question, the one that scientists and engineers and dreamers are asking in real time, even as you rest here and listen, and that question is simply this: can we go to it? Can we, as a civilization barely capable of reaching the outer edges of our own planetary system, find a way to send something, anything, a small craft, a camera, a handful of instruments, out far enough and fast enough to catch a visitor that is already moving away from us at speeds that humble our most ambitious machines? The answer, as it turns out, is complicated and beautiful and full of the particular kind of hope that only emerges when the challenge is very nearly impossible but not quite. Let us think about the geometry first, because the geometry is everything. When 3i Atlas was discovered, it had already made its closest approach to the Sun, already rounded the great curve of its hyperbolic arc, and was beginning the long outbound leg of its journey, a journey that, unlike the journeys of comets and asteroids and all the familiar objects of our solar system, has no return. There is no second passage. There is no opportunity to observe it again in 100 years or 1,000 years. It came, it passed, and now it is leaving, and the window of useful proximity is measured not in years but in months. This is the agonizing calculus that mission planners face. Any spacecraft launched from Earth today would need to travel extraordinary distances and achieve extraordinary velocities just to intercept an object that is already receding. The tyranny of the rocket equation, that beautiful and merciless relationship between mass and velocity and fuel, makes fast missions enormously expensive in terms of energy. To go fast enough to catch 3i Atlas before it exits the inner solar system entirely would require either a very small spacecraft with very little fuel, a gravitational slingshot maneuver around the Sun or another planet, or some combination of both, and even then, the margin is razor thin. But here is what makes mission designers passionate about problems like this one. The challenge is not unique. Scientists have been thinking about interstellar object intercept missions ever since one Oumuamua was discovered and slipped away before anyone could reach it. The painful memory of watching that first visitor depart without a single close-up image, without a single in situ measurement, without the faintest possibility of sending even the smallest probe to take a sample or a spectrum, that memory has driven years of careful, creative engineering work aimed at being ready the next time. The European Space Agency and various academic groups have studied mission concepts with names like Comet Interceptor, which is actually a real spacecraft sitting in storage, not metaphorical but literally a mission that was designed and built in part to intercept dynamically new comets, objects visiting the inner solar system for the first time, but which could potentially be redirected toward an interstellar object if the timing aligned and the trajectory proved feasible. Comet Interceptor is a small, elegant three-part mission, a mothership and two sub-probes that could fly formation around a target, gathering data from multiple angles simultaneously. It carries dust analyzers and spectrometers and cameras and magnetometers, and if it could be aimed at 3I Atlas, the data it would return would be transformative. Then there are the more speculative but increasingly serious proposals for solar sail missions. A solar sail is exactly what it sounds like, a spacecraft pushed not by rockets but by the gentle, continuous pressure of photons, of sunlight itself, pressing against a mirror-thin reflective surface. The great advantage of a solar sail is that it requires no propellant. It simply catches light. And if a solar sail is deployed very close to the Sun, where the photon flux is enormous, the force it experiences is enough to accelerate it to velocities far beyond what a conventional rocket could achieve. A sufficiently large and sufficiently lightweight solar sail, released from a sun-grazing orbit, could potentially reach speeds of several hundred kilometers per second, fast enough, in theory, to chase almost anything. This is not pure fantasy. The Planetary Society successfully flew a solar sail in Earth orbit. The Japanese Space Agency flew their Ikaros mission past Venus. And the theoretical work behind interstellar solar sailing has been done carefully and rigorously by groups who take the physics seriously. The challenge, as always, is in the engineering, building a sail large enough and light enough and robust enough to survive the intense radiation and thermal stresses near the Sun, and deploying it reliably enough to aim with the precision an intercept mission demands. There is also the concept of a laser sail, or light sail, of the kind imagined by the Breakthrough Starshot initiative, where a ground-based laser array pushes a tiny spacecraft to a significant fraction of the speed of light. This technology is still decades from realization, but it points in the direction that humanity is beginning to look, not just at our own solar system, not just at the interstellar objects that drift through it, but at the stars themselves. For 3I Atlas specifically, the observation window is now the most urgent priority. Even if no spacecraft can be launched in time for an intercept, telescopes can still gather data. Every night that astronomers can point a large telescope at this object, they are learning something. The spectroscopic measurements are being refined and extended. The light curve, the subtle variations in brightness as the object rotates and tumbles, is being recorded and analyzed. If there is a coma, that coma is being monitored for changes in structure and activity as the object moves away from the Sun. And all of this data, gathered patiently and methodically by astronomers around the world, will paint a portrait of this visitor that is more detailed and more nuanced than anything we were able to achieve with Oumuamua or Borisov in the time we had with them. The importance of acting now, of observing now, cannot be overstated. Once 3I Atlas passes beyond the orbit of Jupiter, once it crosses into the outer solar system and begins its long exit trajectory toward the heliopause and then beyond, it will fade below the threshold of even our largest telescopes. It will become a point of light, then a faint smudge, then nothing at all, invisible against the field of distant stars it is already beginning to resemble. The chance to know this object, in whatever detail is available to us, belongs entirely to this brief window of proximity. And so the observatories are working. The radio telescopes are listening. The infrared satellites are measuring thermal emission. The optical telescopes are counting photons. And the scientists who spend their days with this data are doing something profound. They are trying to read the autobiography of a world they will never visit, written in light and chemistry and orbital mechanics, delivered to us by an object that had no intention of delivering it and that will be gone before we are finished reading. This is what science does. This is what it has always done. It finds the signal inside the noise. It turns the fleeting into the permanent. It transforms a brief passage through our sky into a lasting piece of knowledge about the nature of things. And slowly now, as the instruments continue their quiet watching, as the data flows from mountaintop to computer to mind to understanding, we arrive at the last and most reflective passage of this journey together. We arrive at the meaning of it all, not the technical meaning, not the scientific meaning, but the deep, quiet, almost wordless meaning that comes from sitting with the fact that we live in a galaxy that is alive with travel and exchange, that the space between the stars is not empty but full, and that the universe is, in its patient and unhurried way, speaking to us. The galaxy is speaking. It has been speaking for 4.5 billion years, since long before there were ears to hear it. It speaks in the language of orbital mechanics and spectral lines and hyperbolic velocities. It speaks in the trajectories of ejected comets and the faint signals of interstellar molecules and the long, slow drift of material from one stellar system to another across the vast, cold, luminous ocean of the Milky Way. Every interstellar object that passes through our solar system is a sentence in that language. Every detection, every measurement, every carefully recorded light curve is a word we have managed to catch before it drifted out of range. We have caught 3 sentences now. 3 visitors. 3 chances to read the handwriting of other solar systems. And each one has been different, each one has carried its own particular accent, its own particular vocabulary, its own mysteries and revelations and unanswered questions, and each one has expanded what we thought we knew about how planetary systems form and evolve and shed their material into the galaxy. One Oumuamua told us that interstellar objects can be strange, can be stranger than our models predicted, can have shapes and behaviors that challenge our categories and force us to reconsider what we thought we understood about the difference between comets and asteroids and things that resist easy classification. Oumuamua was a riddle, and it remains a riddle, and its riddle is productive, because it keeps asking us to think harder and imagine more broadly. 2Ir Borisov told us that interstellar comets exist, that the primordial icy bodies of other solar systems, built from the same raw materials as our own comets, can survive the journey between the stars and arrive here still volatile, still active, still carrying the frozen chemistry of their origin in their nuclei. Borisov was a kind of reassurance, a sign that the universe makes things we recognize, that the processes of planetary formation are universal enough to produce objects that, when we finally see them up close, remind us of home. And 3Ir Atlas? 3Ir Atlas is still being understood. Its story is still being written, and we are watching the writing happen in real time, which is a privilege that astronomers rarely have and that the rest of us rarely appreciate. Most of what we know about the universe we know from objects that are either so distant or so ancient or so thoroughly studied over centuries that the discovery has long been separated from the knowing. We learn about them the way we learn about history, from records, from accumulated scholarship, from the patient reconstruction of events that happened before we were present. But 3Ir Atlas is happening now. It is present tense. It is still inside our solar system, still close enough to study, still active enough to reveal its secrets to anyone pointing the right instrument in the right direction on any given night. And that immediacy, that nowness, is something rare and precious in the long, contemplative practice of astronomy. There is something else worth sitting with as you rest here, something that touches not just the science but the philosophy, not just the mind but something deeper, and it is this: the interstellar objects that pass through our solar system remind us that we are not separate from the galaxy. We are not isolated. We are not an island. Our solar system is permeable, open at all times to visitors from other stellar neighborhoods, other planetary systems, other chapters in the galaxy's long biography. The boundary between here and everywhere else is not a wall but a membrane, and things pass through it constantly, invisibly, and occasionally, just occasionally, visibly enough for us to notice and to measure and to begin to understand. This permeability is both humbling and comforting. It is humbling because it reminds us that our solar system is not unique, that whatever makes a solar system special is not our exclusive property but a feature of the galaxy as a whole, distributed across hundreds of billions of stars and the countless worlds that orbit them. It is comforting because it means we are connected, tethered by orbital mechanics and gravitational interaction and the slow exchange of material to everything that has ever formed around any star in any corner of this galaxy. The atoms in the comets that built our Earth came from the interstellar medium, from the gas and dust clouds that collapsed to form our Sun. Some of those atoms may have passed through other stellar systems before arriving here. Some of the material in 3I Atlas may, in millions of years, be incorporated into the surface of some planet around some star we have not yet visited. The galaxy recycles its matter endlessly, and we are part of that recycling, and the interstellar objects that pass through our sky are the visible, detectable evidence of that process, the pieces of the cycle that happen to come close enough for us to see. If there is life elsewhere in the galaxy, and the question of whether there is life elsewhere in the galaxy is the deepest question we carry, then the permeability of solar systems becomes even more profound. It means that life, if it can survive the cold and the radiation of interstellar space even briefly, might have opportunities to spread that we have not fully reckoned with. The panspermia hypothesis, that life, or the precursors of life, can travel between solar systems on the surfaces of ejected objects, is not as fringe as it once seemed. The chemistry of 3I Atlas, if it carries complex organic molecules, if it carries the amino acid building blocks that have been found in meteorites, would add weight to a hypothesis that asks us to consider whether life is not just a local phenomenon but a galactic one. We do not know. We cannot know, yet. But the fact that we can ask the question carefully, that we can design observations and missions that might one day gather the evidence needed to answer it, that we can point a telescope at a rock from another star and measure its chemistry and look for signatures of complexity, that is one of the most extraordinary things our civilization has ever been capable of doing. And you are part of that civilization. You are here, listening, allowing the story of the universe to settle into your mind and your body like warmth, like the gradual darkening of a sky as the sun descends and the stars emerge one by one in the growing stillness. You do not need to understand every equation or remember every detail. What matters is the feeling, the sense of scale and connection and wonder that this story carries, the way it gently repositions us in the universe and reminds us that we are small but attentive, brief but awake, local but part of something immeasurably vast and old and alive with motion. So let us breathe now. Let the science settle. Let the trajectory of 3I Atlas continue its long arc outward through the solar system, past the orbit of Jupiter, past Saturn's rings, past the cold and distant reaches where Uranus and Neptune drift in their slow, stately circles, and then beyond even those outer planets into the vast dim region where the sun's gravity fades to almost nothing and the interstellar medium begins again, that immense, thinly populated ocean of gas and dust and ancient light that three-eyed Atlas crossed to reach us, and will cross again to leave us, carrying whatever memories it carries of our brief proximity. The telescopes will watch as long as they can. The scientists will measure and model and publish and debate. Future missions, perhaps the comet interceptor, perhaps a solar sail, perhaps something not yet imagined, may one day chase a visitor like this one and return to us data that changes everything we think we know. And future survey systems, more sensitive and faster and wider angle than anything we have today, will catch the next interstellar visitor earlier, and the one after that earlier still, until eventually they become almost routine, numbered and catalogued and carefully observed, each one a new entry in the growing record of what the galaxy has sent our way. But for this moment, for this particular passage of this particular night, it is enough to know that the visitor has come and that we were here to see it. It is enough to know that somewhere out there, at a distance growing by the minute, a dark and ancient object from another solar system is moving through our sky, unannounced, unasked, indifferent to our instruments and our theories and our wonder, and that we, with our curious minds and our improbable telescopes and our deep, persistent need to understand, have caught it in our attention and held it long enough to learn something real. The universe does not owe us its secrets. It does not arrange its objects for our convenience or its events for our observation windows. But sometimes, in the long, unpredictable flow of cosmic time, something falls into view, something unexpected, something from elsewhere, something that crosses the enormous silence between the stars and passes close enough to the small blue world where we live that we can see it, measure it, wonder about it, and in those moments, we are reminded of what we are, the part of the universe that watches itself, the part that asks questions, the part that refuses to let the mystery go without at least trying to understand it. 3i Atlas is leaving. And it is all right that it is leaving. The leaving is part of what it is. It was never meant to stay. It was meant to pass, as comets pass, as light passes, as the breath passes, arriving, dwelling briefly in the space between arrival and departure, and then moving on, carrying with it whatever it was before it came and whatever it has become in the fraction of a cosmic heartbeat that it spent inside the warmth of our sun's embrace. Let it go, now. Let it move outward through the cold and the dark, past the familiar landmarks of our solar system, past the places where the planets mark their patient orbits, past the Kuiper belt and the heliopause and the long, gradual transition into interstellar space. Let it go back to the galaxy from which it came, back to the great river of stars and dust and time, back to the immensity that preceded it and that will outlast everything we know. And let yourself rest now, too. Let the weight of the day settle away from you the way a comet's coma settles and disperses as the comet moves away from the sun, fading gently, losing definition, merging back into the darkness from which it briefly emerged. Your breath is slow. The room around you is quiet. The night sky outside, whether you can see it or not, is full of ancient light, light that left its source before you were born, before this civilization existed, before the earth had a moon, arriving now, this moment, in the same patient way it always arrives, indifferent to time, carrying nothing but itself, asking nothing in return. The stars do not need you to look at them. But they are there when you do. They have always been there. They will be there tomorrow. They were there before the first human eye opened and looked up and felt the first wordless stirring of the question that has never stopped being asked, what is out there, and what does it mean, and are we alone in this great, luminous, endlessly unfolding dark? 3i Atlas is part of that question. It is evidence of the universe's complexity, of the galaxy's restlessness, of the processes that form worlds and break them apart and send their pieces traveling across the void for millions of years until they happen, by the impeccable indifference of orbital mechanics, to pass close enough to a small inhabited world that the inhabitants can look up and say, there, that point of light moving through the star field, that is from somewhere else. That is a traveler, that is a message written in matter and delivered by gravity, and we are trying to read it. We are trying to read it. And in the meantime, in the quiet space between the questions and the answers, in the long night that is also a kind of gift, a period of stillness in which the mind can rest from its reaching and the body can be exactly what it is, warm and breathing and held by the earth and part of the universe in the most intimate possible way, made of the same atoms as the stars, as the comets, as the visitor from another solar system moving through our sky. You can close your eyes now, if you haven't already, and let the darkness be soft and full rather than empty. Let the stars be distant. Let 3-Aya Atlas be in motion. Let the telescopes watch. Let the scientists measure. Let the galaxy continue its immense, slow, incomprehensible work of building and destroying and recycling and sending its pieces on long journeys through the dark. You are here. You are still. You are resting in the knowledge that the universe is being attended to, that the questions are being asked, that the watching is being done, and that tomorrow and the day after and in the months and years ahead, more will be known, more will be understood, and the picture of what we are and where we are and what the galaxy is trying to tell us will become, incrementally, carefully, beautifully, more clear. The visitor moves outward. The instruments grow quiet. The night deepens. And you, here, in this moment, in this darkness that is full of light too faint to see, can let your thoughts slow and your breath deepen and your body sink into the particular rest that comes from having traveled, for a little while, through the immensity of things. Sleep now. The galaxy will still be there when you wake. 3-Aya Atlas will still be moving. The stars will still be burning. And you will be rested, and ready, and perhaps a little more in love with the universe than you were before. That is enough. That is more than enough. That is everything.